If you're trying to undo a product rule, you're going to need a new tool because it is more complicated and it has more pieces. And doubly so because those pieces sometimes during the factoring collect together. So you can't necessarily see the derivative of the first, leave the second alone, plus leave the first alone, derivative of the second. So one like this, for example, x multiplied by ln of x, that doesn't look like the answer to a product rule question, but it's ultimately going to look like one by the time we're finished. So in order to undo a product rule, you need a thing called integration by parts. And integration by parts is just a formula. So I'm just going to write it out. It's going to make no sense and it's going to cause you some stress, but don't panic, it's not that hard. So the idea is that the integral of a thing, I'm going to use v as one of the things, multiplied by the derivative of some other thing by dx is equal to the first thing, the second thing, subtract the integral of the second thing dv by dx. Now later I'm going to show you how product rule turns into this if you try and reverse it. But for now, we're just going to use this model.
Dalton and Marshall return to class now. Dalton, Marshall, return to class.
And we're going to use this model in order to try and tear apart an integral like this. Okay, so first off, I've got this little structure and this little structure. I want to assign one of these pieces to v and one of these pieces to u. So I'm just going to try some random combination. Okay, I'm going to let v equal x and let du dx equal ln x. Okay, so if I use this, if I set v as x and the derivative of u by ln x, I'd put them in there, I would get x ln x dx, so no problem. But over here, I'm going to need to be able to fill in u, not the derivative of u. I'm going to have to fill in the derivative of v, not v. So I'm going to try and get those pieces. This one's not too bad. dv dx is just 1. But here, I'm going to have to ask myself, what function has ln as its derivative? And I can't think of one, right? Not off the top of my head. I'm not sure what that answer is. So I'm kind of stuck if I make the assignments like that. I didn't have to. I could have made this one ln x. And I could have made this one the x piece. So if I put a ln x here and an x here, I would get the integral of x ln x dx. So I haven't changed my setup. But what I have accomplished is that dv dx, I know the derivative of ln, that's 1 over x. And if I ask myself what function gives me x as my derivative, well, that has to be 1/2 of x squared. So I have the pieces I need in order to plug this stuff in. So if I go across on this particular integral, I have the integral of v, that was this, of ln x multiplied by this dx is equal to u, which is this thing, v, which is this thing, subtract the integral of u, which is this thing, dv dx, which is this thing, dx. So that's a mess. You may be asking yourself, why did I do that? How did this help me at all? Well, you notice that the ln is no longer behind an integration, right? It was stuck inside the integrand there, and there is no ln in here anymore. So that's the first thing that it's helped. It's pulled that function right out of the calculus part of this this exercise, and it's left me with an x squared divided by an x. Well, that reduces to just 1/2 of x. So the integral of ln x dx is 1/2 x squared ln of x minus 1/2 of x dx. The other thing it's accomplished is that this is a basic derivative, right? What would give me 1/2 x as my derivative? Well, it would be 1/4 x squared. So I can give that a try. All right, negative 1/4 x squared, bring the 2 in front, gives you negative 1/2 x, which is what I'm after here. So if I do that integration, I end up with the integral of ln x dx, which was the complicated integration I couldn't do at the first part, is equal to 1/2 of x squared ln x minus 1/4 of x squared plus whatever that constant is. Oh, and oops, oops, we're done. So it just, you were able to use puzzle pieces in order to hack this out. Now, I'm going to record this line up here, and then we'll just do a double check to make sure that that actually works out. All right, so if the integral of x ln x dx is 1/2 of x squared ln x minus 1/4 x squared plus c, then the derivative of this thing should be x times ln x. So I'm just going to try that in order to see if it works out. So the first thing I'm going to spot is that I have a product rule here. And that's what this whole thing was about, was undoing product rules. So the first part of my derivative will be the derivative of the first, leave the second alone, plus leave the first alone, derivative of the second one. So the derivative of 1/2 x squared, bring the 2 down, 1/2 of 2 is 1, that's just x. I've got ln x here. Leave it alone. And the derivative of ln x is 1 over x. So I've done the derivative of this piece here by product rule. Now I have this little tag here. That's negative 1/4 multiplied by 2x. And the derivative of a c, right, any constant, is gone. So if I tidy this up a little bit, I end up with x ln x out in front. That's encouraging. It's supposed to be there. An x squared divided by an x is x. And negative 1/4 times 2 is negative 1/2 x. And you see what's happened here. This little tag, this extra piece out here, ended up clobbering half of your product rule, which is why you couldn't see the pieces of the product rule up in that original function. Once that's done, right, 1/2 x minus 1/2 x returns to me x ln x, which is what I was after. So we were able to use this breaking up of an integral into pieces in order to reassemble the pieces into an easier integral to solve. And that's the whole spirit of this, is to take something that's complicated, that you can't do, rejig the bits into a set of stuff that you can solve with basic integrals. And it'll spit out some sort of product rule and then some correction terms at the back in order to make it work out. So I'm just going to clear this off and we'll try another example. All right, this one is a little different. I've got x squared multiplied by e to the x. So I'm going to assign either this as v or this as v. And then as a consequence, whichever one I don't choose as v will be the du dx half. So if you can think ahead to what you're doing, whatever you assign as v, you're going to have to take its derivative. Whatever you assign as du dx, you're going to have to integrate. So if I were to look at this particular integral, I could do either. But only one of them is going to make it more simple. So I'm gonna do both choices, and then we're going to decide which one we like best. So on this side, I'm going to try v equals x squared and du dx equals e to the x. And then over here, I'm going to try setting v as e to the x and du dx as x squared. Okay, so under these choices, if I choose v as x squared, then this puzzle piece is going to be 2x, and this puzzle piece would be e to the x. The derivative of e to the x is itself. Under this set of conditions, if I had chosen e as this part, then this puzzle piece would be e to the x, and this one, the u, would have to be 1/3 of x cubed, because the derivative of this gives you x squared. Now, to decide which one is going to be easier to work with, I'd like you to look at this chunk of the puzzle. The idea was that this is too complicated, so I need to pick puzzle pieces so that my new integration is simpler than the one that I had in the first place. So over here, that chunk, integrate u, which is this piece, and dv dx, which is this piece. That's what my integral will be under these choices. Under these choices, it would be the integral of u, which is 1/3 x cubed, and dv dx, which is e to the x. So I'd like you to look at those two. Do you notice that under these choices, the power on the x right here has dropped? It went from being a parabola to a line. This one increased, right? It used to be squared. Where'd it go? It used to be squared. Now it's cubed. So I've made this higher order. I couldn't solve x squared e to the x, so I'm certainly not going to be able to solve x cubed. I'm not able to solve x to the power 1 either, but if I did it again, right, if I used this integration by parts a second time, I'd be able to eliminate that x entirely. It would go from power 2 to power 1 to power 0. And if you can see it in your head, you'd just be integrating e to the x under these choices. Under these choices, that power of x keeps increasing, and it just gets higher and higher and higher as you go. So there's no end to the sequence of derivatives, right? It just gets higher and higher and higher. So if you are trying to choose between the one to take the derivative of and the one to integrate, if your derivative process will eventually grind a piece away to nothing, then that's the one you want to be taking the derivative of. So I'm going to make these choices because these ones just balloon the problem out. So under these choices, the integral of x squared e to the x dx would be equal to this puzzle piece, which is here, this puzzle piece, which is there, subtract the integral of this puzzle piece here, and this puzzle piece here. Alright, so I'm going to make a new set of choices then. In order to solve this integral, I'm going to need to use integration by parts again, and I've got a 2x there. That thing, if I took its derivative, would just be a number. So that's the one I'm going to choose to grind away. So I'm going to choose that p equal 2x, and that q or dq dx be my exponential part. So under those choices, dp dx would be 2, and q would be e to the x. So what I'm going to do there is I'm going to keep this. That was my original question. Integral of x squared e to the x dx. is this thing was already there because of my first attempt at integration by parts. Subtract. Now I'm going to use this puzzle piece again, using these pieces to try and solve that integral. So the integral of 2x e to the x dx is this piece here, 2x, times this piece here, e to the x, subtract the integral of this piece, which is here, and this piece, which is here. All right, so the integral then of x squared e to the x dx is this piece, because it was already here, subtract 2x e to the x, subtract, which is a plus. Now I can just integrate this. What function would give me 2 e to the x as its derivative? Well, 2 e to the x plus some constant would do that. And there you go. I've generated the answer to this particular integral. So like last time, and this is a good habit, I'm going to take this and pop it up there, and I'm going to take its derivative to make sure I get that as my answer, so that I know that I've done this correctly. All right, this piece is going to require a product rule. If I take its derivative, derivative of the first, leave the second, plus leave the first, derivative of the second. Then I have another one here. This will also require product rule, plus derivative of the first, leave the second, plus leave the first, derivative of the second. That's going to be this one. The derivative of 2e to the x is just 2e to the x, and the derivative of a c is gone. So you're going to have to work this out. Looking at this first chunk, the derivative of x squared is 2x. Leave this alone. Leave this alone. Derivative of e to the x is e to the x. New product rule, derivative of the front thing. Derivative of negative 2x would be negative 2. Leave this alone. Leave this alone. Derivative of e to the x is e to the x. And if I scroll across here, do you notice that I have a subtract 2e to the x and a plus 2e to the x? Those have undone each other. And if you look again, I have negative 2x e to the x and positive 2x e to the x. These two match. One is positive, one is negative, so they have undone each other. And the only term that survives is this one, x squared e to the x, which is what we started with in the first place. So to do this one, I had to identify that the polynomial was the one I should try grinding away. And after I'd applied my integration by parts formula once, I still had an integral that had a product rule in it. So I had to use the integration by parts tool a second time in order to generate the full integration of this particular function. All right. So I'm going to clean this off. We're going to do one more example, two more examples actually, and then we're going to talk about where this formula actually came from. So that looks like it should be a basic function, right? It's just a ln in there. But if you think about it, if you go through the list, what function has ln as its derivative? You're not going to find one. We have a derivative for ln, but not one that has ln as the answer to the derivative. So how are we going to solve this? Well, I bet it's integration by parts. The trick here is spotting that in front of this, there's a little number 1. So the choice I'm going to make for my u and my v values is I'm going to make v the ln x. Because if I take its derivative, it won't be a ln anymore. It will be 1 over x, and that's an easier function for me to manage. I'm going to make the du by dx the 1. So if I make those choices, the other two puzzle pieces would be the derivative of this one, which is 1 over x, and the integral of this one, which is just x. So I'm going to assemble these puzzle pieces into this particular formula. So I have the integral of 1 ln x dx equals this puzzle piece, which is here, this puzzle piece, which is here, subtract the integral of this puzzle piece, which is here, and this puzzle piece, which is there. So this thing, that was just integral of ln x. So I'm going to write it that way just to save us some marker strokes. X ln x is, I don't have to do anything else to that. This is the integral of, well, x times 1 over x, those undo each other. So it's just the integral of 1. So what function has 1 as its derivative? Well, that's just x plus any constant I'd like to think of. So this should be it. This should be the answer. This is the thing that has ln as its derivative. So as always, I'm going to erase this and I'm going to get some space up there. Actually, I might be able to fit it in here. Let's give it a try. So this part, that's going to need a product rule. Plus leave the first, derivative of the second. The derivative of x is -1, and the derivative of any constant is 0. So, working out this product rule, derivative of x would be 1. Leave this alone. Leave this alone. The derivative of ln is 1 over x. X times 1 over x is just 1. 1 minus 1 is gone, and the only piece left is 1 ln x. So it worked. So even though there was just a number in front of there, because the ln was something I couldn't deal with, right? I don't know what function has ln as its derivative, I could squeak that little 1 in there, use the fact that the v puzzle piece takes a derivative to get the second puzzle piece, and eliminate the logarithm from the integral I'm trying to work at. This is a very useful tool when you have logs inside of integrals, is that you can eliminate them and render them as rationals if you put your puzzle pieces together correctly. So one more example with a sine or a cosine, and then it's off to figuring out where this came from. Okay, e to the x is sine x dx. Whew. So if one of those was a polynomial, that'd be the piece I chose for v, because I would grind it away. Well, this one's a bit weird, because if you keep taking the derivative of e to the x, you get e to the x. So I'm not going to be able to grind that away. And if I take the derivative of sine, I get cos. And if I take the derivative of cos, I get sine. In each iteration, this is just going to flip back and forth between sine and cosine. So I'm not going to be able to grind either of these away. So I just have to make some smart choices. So I think it's easier to integrate the e. So I'm going to make it this puzzle piece. I'm going to make v my sine. So if I let v equal sine x, then dv dx would be cos. And so du is the exponential, then u is an exponential itself. So if I fill all those puzzle pieces in, I get the integral of e to the x sine x dx equals u, which is here, e to the x v, which is here, sine x, subtract the integral of u, which is here, and dv dx, which is here. All right, good. Now, in order to finish this, I still have to evaluate this integral, right? I have to do another exponential with a cosine, So I'm just going to blindly go ahead and make another substitution. I'm going to keep them the same. I'm going to let the letter be the trig function, and I'm going to let the derivative be the exponential, because that's easier to integrate. So dp dx would be negative sine x, q would be e to the x. So I'm going to use integration by parts a second time on this particular integral. So I will end up with an integral of e to the x sine x dx equals e to the x sine x minus the p part and the q part, e to the x cos x, subtract the integral of the u part, which is here, e to the x, and the dv dx part, which is here, negative sine x dx. All right. So this thing here then, e to the x sine x dx equals e to the x sine x, subtract e to the x cos x, subtract, 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 that's a negative, the integral of e to the x sine x dx. Okay. And here you're rolling your eyes because this integral is the one I started with. So I'm going to have to keep doing this over and over and over again in a loop. That's kind of annoying. Except for one little tricky thing, if you can catch it. If I added this to both sides, it wouldn't be here anymore. It'd be over there. And because they match, I wouldn't just have two separate integrals. I would have this one plus that one, which is two integrals of e to the x sine x dx. And all I've got left are these pieces here, e to the x, and if I factor it out, I get sine x minus cos x. Well, this was the integral I was asked to find, and there are no more integrations left over here. So I'm basically done. I just need to strip this 2 off. So the integral of e to the x sine x then should be 1/2 of this so you know, everyone's always chirping you to leave this thing on the left side alone and make sure you write it down over and over and over again. Well, this is why. Sometimes this thing that you're working on pops up on the other side, and then you can just collect like terms instead of getting stuck in a never-ending integration death spiral. So if you can see that, a subtract one over here and a positive one over there, you can gather those like terms and come to your solution like so. So I'm going to clean this off, and I'm going to see if we can get to this particular equation from product rule. So I'm going to start with a function. I'm just going to call it f of x. And I'm going to make that function some piece that's a function of x multiplied by some other piece that is also a function of x. So this thing here might be x squared ln x, or square root of x multiplied by e to the x. I don't know. It could be anything. It doesn't matter what those specific functions are. I do know that when I go to take the derivative of this thing, df by dx, I'm going to get a product rule. So I have to take the derivative of the first, and I leave the second one alone. Then I add to that the first one left alone, multiplied by the derivative of the second, like so. Now the next thing I'm going to do is I'm going to multiply everything by dx, because I want to get it out of this denominator. So times dx times dx times dx. So if I do that, all that's left over here is df And this thing here would be, if I write the v first, v of x multiplied by the derivative of the first part with the dx behind it, plus the u dv dx dx. Now I'm going to go through and I'm going to integrate this particular line. So I'm going to integrate here, I'm going to integrate here, and I'm going to integrate here. So this one here, you notice it's got one of those sneaky ones in there, like so. So this little integral here, it's like what function of f, so f is my variable, would have 1 as its derivative? Well, that would just be f. So the derivative of f by f is just 1. And then I have these integrations here. I have integral of the second part of that function multiplied by the derivative of the first and integrated, plus the integral of the first part left alone and the derivative of the second part. Then I'm going to remind myself that this f, the function that I was handed in the first place, was just one piece multiplied by another. So I'm going to write these two things here instead of f. And in the next line, I'm going to stop writing this as a function of x notation because it's putting in too many frickin' brackets. So over here I have u, which was the name of the first part, and v, which was the name of the second part, equals the integral of v du dx dx plus the integral of u dv dx dx. And to try and make it look like this, I'm going to keep this one by itself, kick that one to the other side, so I have u times v subtract this integral u dv dx dx equals the integral of v du dx dx. And that's exactly what I have written up there. So this integration of parts thing is just product rule undone with one integral and then rearranged so that you can use puzzle pieces in order to deconstruct a product rule that you're trying to integrate. So with that in mind, I mean, you don't have to reproduce this, but you're going to be sitting someday in a first year calculus lecture and you're going to be asking yourself, why are we doing this? And that's it. This thing, integration by parts, isn't new. It's just undoing the product rule, right? It literally comes from the structure of that thing. So use this, try the practice problems, and see if you can use this particular tool, identify the right puzzle pieces. You're going to have to play with them a little bit, and until you get good at this, you're going to make the wrong choice a few times. And you'll end up with a new integral that is more complicated than the one you started with. And that's okay if that happens, right? You just scrap it, switch your choices, and see if it gives you something simpler. You might have to apply it twice, you might have to apply it 3 times, and you might have to have like terms that you gather on one side of the equal sign. There's a melange of stuff in there. So give it a try and see how it goes.